Hello, in this video, we're going to be trying to sketch an original function based on either the first derivative or the second derivative. Now, this first example, we're not actually going to do any sketching. We're just going to be trying to think about, okay, what do we know about the original function just based on this thing's derivative? So can we determine where our function is going to be decreasing? Sorry. Well, yeah, that is going to be any place that the derivative is negative. So right down here. When we're going to be concave downward, that is talking about the second derivative. We'll be concave down when our second derivative is negative. So that would be when we have a negative slope. So this region from -7 to -1 will be concave down since that is where the slope of the first derivative is negative. When are we going to have relative extrema? We get extrema when we get our critical values. That is wherever our first derivative equals 0. So these 2 points, we should be getting maximum or minimum. At what values does the graph have a point of inflection? So that is going to be wherever the second derivative equals 0, or where the first derivative has a slope of 0. Those mean the same thing. So right here, we're going to have a slope of 0 on our first derivative. So we'll have a point of inflection uh, on our original function. Again, in this example, we're going to be trying to get some start of information, and then we're going to actually make a graph this time around. We have absolute maximum right here since our first derivative is 0, and we have a negative second derivative, and we can see that this is the biggest value that we have around. Then we also want to check those endpoints to see if we can have an absolute minimum, and yes, we do. Our absolute minimum value is right here, that we would have to check those endpoints. When we're looking for points of inflection, that is where our second derivative equals 0. The only place that the second derivative equals 0 is at these endpoints, so those can't be points of inflection because there's nothing before/after them. So now what we want to do is we actually want to try to make a sketch of this original function. This one's a little bit easier because they kind of give us some starter points. They tell us we got a point at 0, 0. At 2, 0, we've got a point at 1, 2. At 3, -2. So we know that these are all points on our curve. But we want to know, how are we supposed to connect them? This thing is divided into 3 sections. We got 0 to 1, 1 to 2, and 2 to 3. So in that first section, we want to be increasing and we want to be concave down. So we want this curve to kind of like make a downward shape as it's going up. After that point, we are still going to be concave down, but after that point, we're going to start decreasing. So we're going to kind of go warp, heading our way down. Now, at this point, our derivative does not exist, and our second derivative doesn't exist. So something pretty harsh happens at this point. So we want to be continuing to go down, but we don't want to be very smooth. We're looking to make a more sharp point at this spot. So really just kind of like go out straight a little bit and then continue to go down. So it's meant to be like kind of still curving concave down, but not make a very nice spot. In this example, we've got the point f of 0 equals 2, and then we want to use this derivative in order to be able to draw the original function. So we can see after our original spot, we are increasing, we get a maximum, and then we start decreasing by 2. So we want to have like kind of like a maximum point right there. So doing this bit right here, that tells us we want a maximum at 1, and then we want to head back down. So whoop. After that point, we're still going to be decreasing, but we have a point of inflection. So we're switching from being concave down to being concave up. So on this interval, our derivative is increasing, so we want to be concave up. We should also have a minimum value here at 3. So we've been switching from going concave down to now concave up. Now at 4, we have a sharp point right there because we're not differentiable for our first derivative. And so our second derivative is not going to be good. We should still be concave up, but we need to really, really quickly shift to be decreasing at this point. We'll be decreasing until we hit another minimum value a little bit after 5. So right around here, we want to hit a minimum value. So I'm going to go whoop. So still doing concave up so that I can get to that minimum value. And then after that point, I want to start increasing again, but still be concave up. Whoop. So there is my graph. Now I can't really tell like how high those maximums should be or how low those maximums should be. I'm just trying to get estimates of those, but that's about as accurate as we need to be, that we have that sharp point, we have our minimum and maximum values, but how high or how low they go, we don't really know. In this example, we're given the first derivative and we're asked to draw the second in the original function. So if I start at an interesting point for the second derivative, I can draw it pretty easily. We know right on the y-axis, so right here, it has a slope of 0. So right at the x value of 0, the second derivative has a value of 0 because the derivative has a slope of 0. Derivative has a slope of 0. Second derivative has a value of 0. After that 0, then the first derivative is increasing, so it is getting bigger. So after that point, we should have positive values for my second derivative because the first derivative is increasing. Before that point, this thing is going down. And if that thing is going down, that means the second derivative is negative. Using those bits of information, we can determine what should the graph of the original function look like. We know at the point of 0, we have a point of inflection. We know that there is going to be a minimum value right here, and we know that there's going to be a maximum value right here. So we know that this function is going to be going up to a maximum value. It's going to switch from being concave down to concave up at 0, and then after that point, it's going to continue to go up. Now, this might shift up or it might shift down. We don't know exactly how tall that thing is or how low that thing goes, but it should look something like that. It should have that cubic shape because if we took the derivative of a cubic, we'd get a quadratic. In this example, we want to draw the graph of the original function, and they've told us a couple things. It goes through the origin, so we have this point of 0, 0. So we've got a point right there. Then it says that the first derivative is negative when x is negative. So we should have a decreasing function on one side of the origin, and then we should have a positive derivative when x is greater than 0. So we should have an increasing function right here. So we're looking for a smooth curve that goes down and then comes up. Now I could kind of go whap, whap. There we go down, go up. But then this sharp point right there would not be differentiable. And it asked for a smooth curve. So we don't want that to be sharp. We want that nice smooth curve that goes down and then comes up. So that would be the graph of f of x that goes through the origin, that goes from a decreasing function, a negative first derivative, to a positive first derivative being increasing. That sentence got away from me there a little bit. That's the end of our video of sketching original functions based on their derivatives. Reminders that first derivative tells us if the original is increasing or decreasing. And then that second derivative tells us like the concavity of that function and helps us clarify the extrema that we can find used from the first derivative using the second derivative test. Thanks for watching. Hope you took some good notes about the things that I was saying in that video. And thanks for watching. Goodbye. Goodbye.